Okay, for first order solid catalyzed gas phase reactions, we can express the reactions that is in various ways. Suppose we can calculate the rate for unit volume of the catalyst volume if you take Vs, and then we can write that minus 1 by Vs dNA by dt Kr Ca, where Kr is the reaction rate constant, and if you consider the Vs, that is the catalyst volume constant. So, here from this we can measure the rate constant, which is independent of the bed voidage and particle size also. Now, if we because here we are considering the catalytic reactor, here we are not considering the diffusion mechanisms. So, here if diffusion effects we do not consider or do not introduce. So, here it is we can connect or we can link the reactor performance to the fixed bed performance of the fixed bed to the fluidized beds. Now, slide is not changing. 1 minute. Just 1 minute. Slide is not. Huh? Escape is doing. Okay, let me share once again. It is. Yes. So, if you write that that is feed rate is the V meter cube per second of the reactant gas having the concentration inlet concentration CAI to catalyst bed, where the solid volume catalyst volume is the Vs, and now you can integrate the performance expression and if outlet concentration is CaO, we can write for the plug flow reactor 1 minus Xa equal to CaO by Cai, which will be exponential minus Kr tau. Now, for mixed flow reactors 1 minus Xa CaO by Cai equal to minus 1 by 1 plus Kr tau. Now, here where the reactor ability that is to measure is the tau, which will be volume of the catalyst or the solid particles divided by volumetric flow rate of the gas. So, Vs by V. Now, the dimensionless reaction rate will be Kr into tau. So, which will be Kr, which this equation we will be using in the numericals, that is the volume the dimensionless reaction rate Li into 1 minus epsilon I divided by U0. So, here volume of the catalyst means how much if you take the length of the bed Lf, now it will be 1 minus epsilon f and divided by volumetric flow rate of the gas. So, then we can get this dimensionless reaction rate. As I told, depending on the particle size, the catalytic reactors we divide in the 4 groups also. Now, first is the if Geldart A particles we are considering, where the models for the vigorously bubbling fast bubble means a small bubbles will be forming, fine particles Geldart A not cohesive, fine particles are taking. So, here thin cloud will be forming. As I told that is, so in the fluidized bed we can say that it is consist of the emulsion phase and the solid phase. Suppose the or the bed that is when the it is uniformly fluidized all along the bed, solid materials is there, we can say that almost it is the it is the emulsion phase only, means solids in the fluid state it is there entirely. So, it is the emulsion. Now, in this figure we can say it is the bubble phase and it is the emulsion phase, and it is surrounded by the thin clouds. You can see this thin cloud is formed by the gaseous reactant. When the gaseous reactant pass through the bed, that is you can see here CAI. Now, initially small bubbles will be forming, because here pores are there in the distributor. When the gas is flowing through this, small bubbles will be forming, and these bubbles coalesce with each other, tend to form the larger particles. But what happens here, as it is the bubbling bed for vigorously bubbling, as continuously bubbles will be forming, that will be moving. Now here, as the bubble movement or bubble speed is faster than the gas velocity, here you can see bubble for this is the condition that the bubble velocity with which bubble is rising is greater than the minimum fluidization velocity. So here the this gaseous reactant form the cloud here, means surround the bubble, a thin layer is formed surrounding the bubble. Then when the bubble will be moving, that cloud also slowly moving, and here in this below this bubble, this will be the wake region. That is morning sir was saying also, whether it is the liquid 3 phase or the 2 phase. So in this region will be the wake region, in where the some solid particles, because some pressure difference is created when the bubble moves through that wake region, the some solid particles are dragged into this wake region. When the bubble moves, those solids also move with that. Now here bubble moves faster and than the superficial velocity. So by which what happens, when the bubble will be moving faster, so thin clouds will be again on the top, it will be broken, and then it will be moving again, another cloud will be forming, because it is continuously fluidized. So on the upper region also some gas or gaseous reactant already there. So here you can see that in the cloud region, this is the cloud region, this is the emulsion that is in the bed, it is the solid particles is getting fluidized throughout the bed, it is there emulsion region, and this is the bubble is there. So here thus if you consider any section wise for any height, you can see here the how the movement is, bubble is moving at this bubble velocity, and here the cloud to emulsion, you can see cloud to emulsion, the gaseous movement is there, means it is reversible, emulsion to cloud, cloud to emulsion, and here you can see bubble to cloud, from the movement gaseous reactant movement will be there, bubble to cloud, cloud to bubble, and then cloud to emulsion, emulsion to cloud. Again here you can see some gaseous reactant here from the bubble to entering the cloud, constantly it is entering the that is emulsion phase also. So with this mechanism reaction takes place. So here basic principle is that overall disappearance in bubble will be reaction in the bubble plus transfer to cloud wake. As I told, when the gas is entering the bubble is moving at a faster speed. So naturally the disappearance in the bubble, overall disappearance, the gas will be when the bubble will be moving, the gas will be forming again the cloud for the successive bubbles which will be coming out from the lower region. So thus there will be some within the bubble also some solid particles are there. So reaction in the bubble plus, because reaction of the gaseous reactant with the solid particles which are already present in the bubble, and transfer to the cloud wake region also. Some solid particles are the gas are there in the cloud region. The gas also, when the bubble moves out, some gaseous reactant also flows to the comes to the wake region. That is in the cloud, lower part of the cloud is the wake region. So there in the wake region also some gases transferred. So transport from the cloud to wake region we can break again into two components, that is reaction in the cloud wake region, because cloud wake region also particles are there. So with that also the reaction is taking place, again transport to emulsion. So some gaseous reactant is getting transferred to emulsion. So that's why in that figure we saw it is reversible, cloud to emulsion, emulsion to cloud. Then transport to emulsion, it is the in the emulsion phase it is transferred to when gaseous reactant is there either from the bubble or from the lower region. When the gaseous reactant is moving to the directly to the emulsion, there will be reaction in the emulsion also. So this is the first type of the reactor, how the as bubble moves faster than the gaseous reactant, reaction is taking place all cases, that all places, that is in the emulsion, in the bubble, as well as in the cloud wake region. So, second type of the reactor will be for a bubbling bed of the intermediate size particles. Intermediate size particles means it will be AB category, means slightly means larger than the B, but clearly not the B, it is AB, intermediate size particles is there, where you can say that UMF by epsilon mf, that means you can say that fluidization velocity UF will be UMF by epsilon mf is less than the bubble velocity, but it is less than 5 times the fluidization velocity, means it is more than the bubble velocity is more than the fluidization velocity UF, but it is less than the 5 times the fluidization velocity. Here you can see for intermediate size the bubble movement slows down, the here you can see bubbles is there, the gas is moving faster. So, here bubble to cloud, and that is why what happens, instead of forming the cloud, here immediately gas considers this gaseous reactant which comes from the bottom, it uses this as a bubble, as a shortcut, shortcut path, enters it and leaves at the top, because gaseous reactant is moving faster than the bubble. So, it leaves the top of the bottle and top of the bubble and moves faster, and finally that is leaves the fluidized bed. So, thus here when it is leave the bubble, because entering from the bottom of the bubble, as gas moves faster, gas speed is more. So, here what happens, it comes out, using the bubble as a shortcut path and comes out of the bubble, then in the emulsion the reaction will be taking place. You can see the gas is entering and coming out. Here you can see where the in the emulsion, that is the fluidization velocity will be UMF by epsilon mf, and this is the UB, and here the means almost cloud will be broken. It is so you can see that in the what is the mechanism. So, there in the we saw that cloud formation was there. So, first order irreversible catalytic reactions on accounting of the reactant gas A as it passes through the two sides, two side by side regions, it gives disappearance in bubble, that is reaction in the bubble, transfer to the emulsion, and this transfer to emulsion will be reaction in the emulsion and transport to bubble. So, cloud part is not there, as because it is moving, gas is moving faster than the bubble. Third type of the reactor, where it is bubbling bed of the large size particles. So, here further the bubble movement also slows down, because when the particle size is small or the fine, the bubble moves faster than the gaseous reactant, but when the size increases, the bubble speed gradually decreases, or we can say that gaseous reactant moves faster. So, here you can see also it follows the path this PQ, means it is entering, and here also it is leaving, means it is successively entering the bubbles and the leaving at the top, and here in the bed is almost you can say divided into the two phases only, means there in the intermediate size particles some thin cloud might be formed, but here cloud will not formed at all. So, here you can say that is rise velocity of the gas in the bubbles UV star, it is saying will be bubble velocity plus 3 times the UMF. Here UV bubble velocity is less than the fluidization velocity, it follows the path P to Q, which shows the behavior of a typical element of the gas, that is at any level of the bed the distribution flows between the gaseous reactant and bubble will be U0A will be that is fluidization, that is superficial velocity into the area of the reactor. Or the bed area, you can say, flow through the emulsion plus flow through the bubble. How much gas is entering, that much is passing to the emulsion, and and also flowing through the bubble. Means at any time, if you see the gaseous reactant, either it will be summation of the if particular element if we are considering in the emulsion phase and in the bubble phase. So, which is 1 minus delta into UMF into A plus delta UB plus 3 UMF into A, where from where here we can say that is the bubble delta is the bubble fraction, which is U0 minus UMF by UB plus 2 UMF. So, bubble fraction, that is how much bubble fraction means how much portion of the gas is remaining in the bubble, that we can say. So, here the fraction of the gas that passes through the emulsion and contact the solids, when it is passing through the emulsion, where in the emulsion it is the gases, the solid particles are there. So, the gaseous reactant is in contact with the solid particles constantly, it is in the contact with that. So, that fraction of the gases which passing through the emulsion phase, and that is the delta will be passing through the bubble phase, and here it is the fraction passing through the emulsion phase, which we can calculate as 1 minus delta UMF by 1 minus delta UMF plus delta UB plus 3 UMF, where UB is the bubble velocity, UMF minimum fluidization velocity. So, which will be solving this UMF by U0 1 minus delta. Now, if you ignore the conversion in the bubble phase, means there is no conversion, because very little amount of solid will be there in the within the bubble solid particles. So, we can ignore that, those solid particles are not reacting or the not getting converted. So, this equation which represents the fraction of the bed solids contacted by gaseous reactant as it passes through the bed, then only you can say that it is the fraction of the gas in contact with the solid particles. So, comparing this equation with the plug flow expression, which we discussed, fast plug flow and mixed flow reactor expressions. So, then we can write this performance expression in this regime of the reactor. 1 minus XA will be here plug flow we had written, that is it is the rate reaction rate 1 minus means how much fraction is getting converted, 1 minus XA CaO by CaI, which is exponential minus Kr tau into fraction of the gases which is in contact with the solid. So, thus here 1 minus XA. So, substituting this fraction here we can write it is 1 minus XA is exponential minus Kr, and in place of the tau, as it is the volume by volume of the solid particles divided by superficial velocity LF 1 minus epsilon F by U0 into this UMF by U0 into 1 minus delta. Here 1 minus delta is there. So, thus we can get now comparing to the plug flow reactor efficiency. Here the efficiency also we can calculate for this reactor model 3, it is the for the large size particles UMF by U0 into 1 minus delta. You can get the efficiency also. As under the minimum fluidization condition, the bed voidage epsilon MF is about 50% of the bed volume, that is 0.5. So, and also we know that this UMF by epsilon MF is greater than the bubble velocity, this type of the reactor, where we can determine that how delta cannot exceed reasonably 0.25 to 0.35, because if we are exceeding this epsilon MF will be exceeding the 0.5 also, but epsilon mf cannot. With this we can substitute in the expression for the delta, we can check that, because delta cannot exceed 0.25 to 0.35 in this contacting regime, and the only when u0 is 2 to 2.5 UMF. So, if you take u0 2 to 2.5 UMF, we can check this delta. u0 is, if you are taking 2 to 2.5 times UMF, if you are substituting here 2 times u0 as 2 times UMF. So, it in the numerator only one UMF will be there, and here UB also, as it is u0 2 to 2.5 velocity times. So, here epsilon mf we can calculate delta, here it is not should not cannot exceed with these conditions. Here substituting again ub bubble velocity, here it will be u0, if we bubble velocity also we take nearly the 2 types the UMF, it will be 4 UMF. So, here it will be UMF by 4 types UMF. So, thus it will be 1 by 4, that is 0.25. So, here we can see that this is the delta should not exceed. If it is we are exceeding u0, so then it will exceed these conditions. So, for which what happens, the here epsilon mf will also be exceeding that. So, but it is nearly equal to 0.5. So, we cannot exceed more than that. At higher superficial velocities, if we take the higher velocities, that is more than this 2.5 UMF, then there will be channeling, slogging or explosive bubbling will be there, which will replace the ordinary bubbling behavior. That means, here the channeling means this the bubble phase whatever is there, it will be more, means the layer wise solid particles will be there, the entire column will be the entire cross section of the column will be filled with the bubble. So, as a result the top layer, one solid top solid layer will be there, middle another layer, and that way different layers will be there which are not in contact with each other. As a result, uniform mixing or the uniform heat transfer, mass transfer will not occur. So, that is the slogging. Or channeling means all the bubbles will be forming in a will be there in a line, in a vertical line, that a channel will form, that also will affect the fluidization phenomena. So, if you are taking the this velocity, superficial velocity more than the 2.5 times the minimum fluidization velocity, then channeling, slogging may occur, or more bubbles will be forming, explosive bubbling will be there. So, ordinary bubbling behavior will be affected. So, one example will be solving. Before that, just last type of the reactor, which will be where also gaseous reactant gets converted, that is the reactor model for the freeboard region, that is above the bed, as yesterday also I was telling the freeboard. So, here the when the solid particles are there in this the solid initially when fluidization takes place, some before the takes place, whatever the material is taken, that is the bed volume is there, and when the fluidization takes place, some of the particles will be forming or moving up to certain level, but beyond that, that is the region that will be the splash zone, that is it will be expanded, and just within that it will be fluidizing, and beyond that what happens, it is the very fine particles or the lighter particles will be moving up, and that is the freeboard region, and some solid particles may go there also, but immediately they fall down because its gravitational force, that is the terminal velocity, may exceed the superficial velocity, because of which these particles may fall down. So, here this in what happens, as the gas solid contact increases, here the it is researchers found that here the some gaseous reactant is moving, along with that some fine particles or the some coarse particles also moving. In this region also, where very small quantity of the particles will be there also reaction will be taking place. So, that is the freeboard region reaction takes place. So, above the fluidized bed, and here and researchers show that contact efficiency between the catalyst and the reactant gas increases. This as contact they also remain in contact in the freeboard region. There also the reaction takes place in the freeboard region. On this basis, the Kuhnel-Levenspiel, the researchers, they presented a reactor model, that is this fourth model, for estimating this added conversion in the freeboard region. In addition to the main bed region, whatever reaction is going on, again some reaction also is going on in the freeboard region. So, although the freeboard region, the concentration of the solid is very less, it is that can be extended to the relatively dilute contacting of the fast fluidized beds. So, thus here also the that is letting the density of the particle, if you are taking at any level ZF in the splash and the freeboard region, the then mean density if you rho bar. So, here we can write the mean density will be rho 0, that is whatever initially we have taken, rho 0 into exponential minus A into ZF at any height ZF. So, this is the fourth type of the you can see here the efficiency as versus the bed height it is taken. So, thus here the mean density is to be considered, because in the bed region density will be higher and here in the freeboard region density will be less also. So, mean density is to be calculated, based on that efficiency can be calculated. Now, one numerical will be just because four types, four reaction examples are there, but just one I just considered one, because it will not take not be possible to solve all the four reactor examples. So, this is the suppose Geldart B particles are fluidized at the fluidization velocity of the 0.25 meter per second in a baffled bed, where the bubbles are kept small and bubble diameter is 0.025 meter. So, thus conversion factor, we have to calculate the conversion factor. For reaction rate constant is the 1.5 meter cube per gas per meter cube catalyst per second. So, here data given. So, for gas diffusivity is given 9 into 10 to the power minus 5 meter square per second, and particle density is 325 micron meter. Now, the mean voidage is 0.42, which is you can say that in the fluidized condition also, that is epsilon m f same, that is Lm length of the fluidized bed 0.8 meter, and minimum conditions the fluidization voidage is 0.45 and minimum fluidization velocity is 0.21 meter per second, and gamma b that is 0. So, here for this we need to calculate the conversion, how much gaseous reactant is getting converted. So, here let me share the whiteboard, that we will be doing. So, here yesterday I was saying that some bubble velocity UV, how we can calculate, and sorry bubble rise velocity. So, here UVR, U subscript UVR, it is just I was telling, but not 0.711 1 minute. 0.711 into G dB to the power half. It is the bubble rise velocity. Now, the bubble velocity will be UB U0 minus UMF plus UBR. How it is coming? See, U0 means how much at what velocity the gas is coming, a superficial velocity from the bottom. UMF at what velocity it is getting fluidized, the solid particles are fluidized. That means excess velocity whatever is there, that will applying some extra pressure on the bubbles to move up, plus the bubble rise velocity if you write. So, then we can get the bubble velocity, that is the excess velocity above the minimum fluidization plus the bubble rise velocity. So, that will be the bubble velocity with which it is moving. So, here the substituting this as bubble diameter is given. So, UBR we can calculate. So, UBR will be 0.711 into G 9.81 into bubble diameter 0.025 to the power half. So, UBR is coming, calculating, it is coming 0.3521 meter per second. So, bubble velocity is, we can write here one line you can give. Now, U0 superficial velocity is given, minimum fluidization velocity also given. Now, we calculated the bubble rise velocity, thus we can calculate the bubble velocity. So, bubble velocity U0 superficial velocity is given 0.25 meter per second, 0.25 meter per second minus minimum fluidization velocity is given 0.21 plus bubble rise velocity which is 0.3521 meter per second. So, adding this is coming, bubble velocity is coming 0.3921 meter per second. So, bubble velocity we got, bubble rise velocity we got. Now, comparing this bubble and the emulsion velocities. Here emulsion velocity UF we can calculate, and that is which will be UF, which is UMF divided by epsilon MF, that is fluidization velocity with which both solid and the gas is moving, that is the emulsion velocity also. So, here bubble and emulsion comparing this bubble velocity with the emulsion velocity. First emulsion velocity you can calculate, which is UMF by epsilon MF, that is UMF is 0.21 divided by epsilon MF is 0.45, it is given. So, emulsion velocity is coming 0.467 meter per second. Now, UB by, when we are comparing this UB by UF, what ratio it is coming? So, let me find out the eraser first, let me rub this. Now, UB by UF, when you are comparing this UB by UF, this is coming 0.3921 divided by 0.467. So, this is coming 0.84, this is less than 1. UV by UF, that means bubble velocity here as it is coming less than 1 means bubble velocity is less. Here the fluid velocity, the emulsion velocity is more than the bubble velocity. So, when your UV by UF is less than 1 indicates that reactor is operating in the slow bubble regime, which we discussed, that is the when the particle size increases further, the bubble velocity slows down. So, here it becomes the 0.84 as less than 1. So, it is operating in the slow bubble regime. So, here delta we can calculate, because we need to calculate the Kr dimensionless reaction rate also, that is Kr tau. So, for which we need the delta. So, delta we can first find out, that is U0 minus UMF by UB plus 2 UMF. So, when you are calculating, that is substitute now U0 we know, UMF we know, UB calculated, so we can calculate this. So, it is 0.25 minus UMF, that is 0.21 divided by 0.3921 plus 2 into 0.21 UMF. So, this is coming 0.0493. So, fraction of the gas in the bubble, it is coming as the delta, it is 0.0493. So, now the reaction rate that is for the plug flow reactor, considering that. So, 1 minus x a we can calculate. So, let me rub this. So, 1 minus x a for the plug flow reactor model, we are considering equation which is exponential minus K R tau. In place of the tau we can write L F, that is volume of the bed, 1 minus sorry L F into 1 minus epsilon F divided by U0 K R into tau. This is the tau expression, because volume of the solid, how much time it is remaining in the bed, residence time of the solid particles. So, L F into 1 minus epsilon F, that is the volume of the solid particles, and this is the superficial velocity. So, this much time tau it is remaining in the bed, so, into your U0 by UMF into 1 minus delta. This expression already we have discussed, that is this will give you the 1 minus x a. Now, all the data we know, so we can calculate this 1 minus x a as exponential, substituting all the values, minus here K R is given, K R 1.5 meter cube of the gas per meter cube catalyst per second. So, minus 1.5 into L F 0.8 is given into 1 minus epsilon F is given 0.42 divided by U0 0.25 into, just let me rub this, this term we have to multiply now. U0 by UMF 0.21 by 0.25 into 1 minus delta, delta already calculated 0.0493. So, thus this is coming 0.1084. So, your 1 minus x a is 0.1084, that means 1 minus x a means how much not consumed. X a is fraction getting converted. So, 1 minus x a not converted. Now, x a we can calculate from this. So, 1 minus 0.1084. So, this is coming 89.2. That means, here gases conversion is 89.2% it is coming. Now, the dimensionless reaction rate we can calculate, which is Kr into tau. So, Kr is 1.5 into tau, it is 0.8, that is Lf into 1 minus epsilon f, which is 0.42 divided by U0, which is 0.25. So, thus this is coming 2.784. So, dimensionless reaction rate constant we got 2.784. Where it is reaction rate constant it is given, and that is dimensional, which is 1.5 meter cube per gas, meter cube of the gas per meter cube of the catalyst per second. So, X A we got, that is percentage of conversion is 89.2%, gas is getting converted, and the dimensionless reaction constant is 2.784. This is for the third type of the third model, which is the large size particles, that is we considered. So, yes. So, thus we got calculate the conversion we calculated 89.2, and dimensionless constant also we calculated. Now, this is here slide. So, so, reactor model for the bubbling bed of the large size particles, where the bubble movement is slow. Similarly, for the other also you can do, but it is time will not permit, just 2 minutes I will just say that here. All cases we are considering the plug flow in the fluidized bed reactors. The models we consider is the plug flow reactor. Suppose we consider the calculation is there. Suppose here another example is there, but question I have not typed here. In the first type model where the for the fine particles, just the last things you can see. Bubbling bed model for vigorously bubbling bed, where the bubble velocity is much higher than the UMF. So, we can just write the last here the reaction rate, it is Kf, it is given by, as lengthy there, I just simply small example one considered, gamma b into Kr. For the fluidized bed, the final rate constant reaction rate will be here gamma b into Kr plus 1 by K B C plus 1 by, I will just explain this and with that we will finish, gamma C into K R plus 1 by K C E plus 1 by gamma E into K R. This is the, because here there in the model, as I told, the bubble to cloud, it is the reversible cloud to bubble, bubble to cloud, then the emulsion to cloud, cloud to emulsion. So, all the again the emulsion to bubble is there. So, that is why here B C, that is bubble to cloud. So, reaction rate constant when the gas is moving from the bubble to cloud. So, reaction rate constant bubble to cloud. Now, it is the reaction rate constant in the cloud only. If you Kr, if multiplied with the fraction which is remaining in the cloud, and it is the cloud to emulsion, then it is the fraction remain for the gas remaining in the emulsion, gamma E into Kr. So, thus here it is in the bubble, fractions remaining in the bubble. So, thus it is as in the different phases reaction takes place. So, here the final reaction rate, because in the reactor it is when one will calculate the overall reaction rate, one will calculate, it is not that how much is bubble to cloud. So, that separately we will calculate, again finally we add all the things. So, here emulsion, then cloud to emulsion, whatever the movement is there across the boundary, then the in the cloud also some reaction taking place, and the bubble to cloud, and then the in the bubble also. So, taking the all this, the Kf is calculated, then 1 minus Xa is calculated, which is exponential, as it is same, I told that it is the plug flow reactor is it is considered Kf, that is overall reaction rate, into delta Lf divided by U0 U0. So, which is equal to exponential minus Kf into Lf by UB. So, this is for the first model. Now, for the second model, just similarly you can, where the intermediate size particles are there, here in symbols we can write here where the second type of the model intermediate size particles, we can just, it is the 1 minus delta into UMF equal to 1 minus delta into 1 minus epsilon mf into Kr into CaE minus delta KBE into CAB minus CAE. So, here as I told, cloud will not be there. So, bubble and the emulsion will be there. So, it is the concentration of the gas in the bubble CAB, concentration of the gas in the emulsion, and here the fraction of the gas remaining in the bubble delta, and here thus we can knowing this, from this we can get the Kr reaction rate, and whatever the reaction rate will be there, if you multiply with the time tau, then we can get the dimensionless reaction rate. So, third type we know. So, fourth type, third type the example we discussed. Fourth type, as it is in the freeboard region, the KFF, the bubbling bed model, where it is KFF in the freeboard region, sorry, 1 minus x, last one we can write instead of writing this 1 minus x a, that is after means how much gas remaining from that constant fraction, that is 1 minus x a is exponential minus k f f into delta L f divided by u 0. So, here first K f f we can calculate, which is in the core region, that is in the main bed region. What is the gamma fraction remaining, reaction rate constant will be plus 1 by K dash B e plus 1 by gamma wall into K r. So, overall that is as in the main bed region some reaction is taking place, and also freeboard region reaction is taking place. So, it is in the when the transfer is there from the bubble to emulsion, bubble movement is also there, but not much. So, it is K dash B e. So, bubble across the bubble and the emulsion, because fluidization always takes place because of the bubble, whether the fast moving or the slow moving bubbles, or the bigger size bubble or the smaller size bubbles. So, here it is the across the bubble emulsion boundaries, it will be K dash, plus it is the fraction of the gas remaining in the core region, main bed region, in the wall region means here in the freeboard region. So, thus we can get the overall that is reaction rate, and substituting that we can get the 1 minus x a. So, this is about the fourth type of the, that is where the in the freeboard region also reaction will be taking place. So, this is some thing, some just in short about the different type of the catalytic reactor, where the gaseous reactant gets converted and the reactions proceeds, and thus knowing all this we can apply this knowledge for the treatment of the gaseous effluent, because if how much gases, knowing the conversion of the gaseous reactant, we can use first if we collect some gaseous effluent or we install the fluidized bed reactor, whether catalytic or the non-catalytic. Usually for the treatment of the gaseous effluent, it is better to use the catalytic reactors. So, that knowing that concentration of the gaseous pollutant in the industrial effluent, gaseous effluent, we can treat in the fluidized bed reactor, where how much gas pollutant from the gas is getting converted, and that we can calculate. Accordingly, we can estimate what is the initially we can carry out the experiment in the bench scale model, then accordingly we can design the pilot plant unit which can be installed in the industries, such that so that the gaseous effluents can be treated properly before emitting directly to the atmosphere, which will save the environment to some extent. So, this is all about this in brief about the catalytic reactor and its role in the treatment of the that is gaseous effluent, and in turn to we can move a step to have a sustainable environment. We can stop here. Okay. Thank you all.